This is section 13.2 and this is example 5. And now what we're going to do is we're going to add a third variable to our integral. So we're going to do x, y, and z. And what you're going to notice in this is that the formula that we used with just x and y is really similar to this one. We're just going to tack on that element of z, that component, and so the entire formula that we used before is exactly the same except that additional component. And just remember that this large line integral here can be simplified to be the integral in terms of the vector r. And in this case, r of t is the vector x of t, y of t, and z of t. So what you're doing is you're changing your function to be in terms of r of t, that vector, and then you're tacking on the magnitude of that because of the transition from arc length ds to dt. Okay. Now remember, we could also integrate in terms of x, y, and z. And so, if you have a line integral that is going to look like this, where there are three different types of differentials, so you have dx, you have dy, you have dz, the easiest thing to do is probably turn it into a large single integral of one variable t. But you could potentially turn all of them into x, or all of them into y, or all of them into z, and then integrate. But again, because there are these three different variables, the best option usually is to just convert everything to t's and basically go this route. Okay, so we're going to tackle example 5 here, and example 5 is the line integral of y sine z ds, and c is the helix given by that equation, which we used a whole lot in our earlier chapters, and then t is between 0 and 2 pi. So we have, just to kind of organize here, we have r of t, this vector, which is cosine t, sine t, and t, and then we have r prime of t, which is negative sine t, cosine t, and 1. And we do need the magnitude of r prime at some point here. So the magnitude of r prime is the square root of sine squared plus cosine squared plus 1, and that simplifies to the square root of 2. Okay, so let's go ahead and put all of this into our line integral formula. Remember, what we're going to do here is change everything to terms of t. So the integral is going to go from 0 to 2 pi, and then we have y in the original, and y is now sine of t. So we have sine of t, and then we multiply by sine of z, but z is just t. So we have sine of t times sine of t, and then remember ds here. ds is going to be the magnitude of r prime times dt. So we have times 2 dt. Okay, if we simplify this, we get, sorry, let's go back. I got to change this. Hold on, it's not 2, it's the square root of 2. So the square root of 2 times dt. Okay, so let's simplify this. We have the square root of 2 times the integral 0 to 2 pi times sine squared t dt. If you all remember, we did a couple of these. We added them on our note cards a while back. The integral of sine squared of u du is equal to 1/2 u minus 1/4 sine of 2u plus c. That's a little formula that was in the back of our textbook that we added to our note card along with cosine squared and others. So to do this problem, it's probably easiest to use that formula instead of integration by parts. So what we have is the square root of 2 times 1/2 t minus 1/4 sine of 2t, and we're going to evaluate this from 0 to 2 pi. And that gives us the square root of 2 times 1/2 times 2 pi minus 1/4 times sine of 4 pi, which is going to be 0. minus the square root of 2 times 1/2 times 0 minus 1/4 times sine of 0. So all of that, all the stuff in that second part is going to be 0. So what we get is the square root of 2 times 1/2 2 pi, which is just the square root of 2 times pi. Okay, so there you go. That's example 5. The next video will be on example 6.